Welcome to the Further Mathematics online revision series, proudly supported by Texas Instruments Australia. Make sure you've got your revision sheet ready to go. So let's get started. Question 1. The heights of a population of Year 12 students is normally distributed with a mean of 170 centimetres and a standard deviation of 5. A student selected at random from this population has a standardised height of negative 2.5. To understand what that figure means, let's have a look at the standard normal distribution. The standardised value of negative 2.5 sits about there on our standard normal distribution. The question wants to know, where is it on our distribution? To calculate this value, we use the formula z equals x minus mu over sigma. It's a relatively trivial use of our solve command, but let's go ahead. So we'll select solve. We put in our standardized value. I'll use the fraction tools, and we're looking for an observed value x minus our mean of 170 divided by a standard deviation of 5. Solving for x gives us 157.5, which of course rounds to 158. That leaves us with the answer of D. Okay, question 2. Another student is randomly selected from the same population and has a standardized height of 1 centimetre. This time we're required to find the percentage of students that are shorter. That corresponds to the area shaded on our standard normal curve, or on our population around there. Looking at this diagram, we can clearly cross off answers A, D and E because they're 50% or less. Now there's a couple of ways we can do this calculation. I'm going to use my previous calculation and convert the standardized value of 1 into our population and see that the answer is 175. So I'm required to work out what proportion of our student population has a height less than 175. I'll go from negative infinity, that's pretty short, all the way up to 175, a mean of 170, standard deviation of 5, and see that that percentage corresponds to about 84%. So my answer is B. Question 3. A sample of 300 students was selected from the same population. This time we're interested in the number of students that are likely to have measured between 165 and 180 centimetres. That corresponds to an area approximately equal to that shaded in our distribution. So let's see how to do this on the calculator. I'll go back and select my normal CDF from the probability menu, and we'll put in our boundary conditions, 165, our upper limit of 180, our mean of 170, and a standard deviation of 5, and see that the proportion is equal to approximately 82%. We'll grab that, multiply it by our 300 students to get our answer, which aligns to option A. Question 4. This time we're looking at a scatter plot. This scatter plot shows a relationship between the number of hours a student spent studying for their SAC and their corresponding SAC score. The question asks us to find the residual value corresponding to the student that spent 3 hours studying for their SAC. Now, whilst the calculator is able to automatically measure residuals, we don't need it for this particular question. We can see directly from the graph that the student that spent approximately 3 hours studying for their SAC scored 15. So we're interested in how far they are from the general trend. We can see that they're about 3 point scores above our line of best fit. This leads us to answer D. Okay, question 5. We're still looking at our scatter plot, but this question asks us to consider the equation to the least squares regression line. Before we work that out, let's take a moment to understand what that line represents. we would expect a natural variation to exist between student study scores. What the line is telling us is a part of that variation is attributable to the number of hours students spent studying. The more time, the better the score. We're seeing a positive correlation. We could work out the equation using traditional techniques. We don't know the data points, but we could approximate them. So I'm going to use a graph application, and I'm going to set the window settings to match those provided in the chart. So I'll go from 0 to 10 on the x-axis, and then 0 to 20 on the y-axis, or student SAC scores. The next thing I'm going to do is just drop in 2 points. I don't have time to draw all of them, so I'm just going to put in 2 points that represent points that are close to our least squares regression line. So I'll need to work out what their coordinates are. I can use the Actions menu, Coordinates, and on the other point. Now I'll move these points in just a moment. The next thing I'm going to do is draw a line. Make sure it's a line, not a segment. Make sure your line falls on both of those points. Then I'll use the Actions menu to get the equation to the line. Now all I need to do is move those points so they're representative of some of the points close to our regression line in the chart. Around about 0.8 was our first one, and at the other end of the scale we saw on about 10 and 20, almost the very top corner. So we can see the equation to our line is approximately 1.2 times x plus 8. So that means our option A is correct. Question 6. In this question, we're required to calculate the correlation coefficient R, given the coefficient of determination. Before we do this, let's just go back a step. Remember that there is a natural variation in study scores. The coefficient of determination, or R squared value, is the proportion of the total variation of y in the sample that can be attributed to our linear relationship with x. So that's our R squared value. We can see it's a positive slope. So when we're calculating R, that is the square root of 0.726, we need to make sure that our answer is positive. You should be able to see that there's no other options left but option B, but let's double check by calculating the square root of 0.726. We arrive at 0.85, which of course is option B. In questions 7 and 8, we're supplied with a set of data. The first part of question talks about linearizing the data. So let's have a look what it means to linearize data. I've already stored the data points, just to save time, in the statistics editor. So we'll go ahead and insert a data and statistics application, just so we can see what the relationship between the x and y variable looks like. I'll use the tab key to access my independent variable, and again tab to get my dependent variable. And I can see that the data does not look linear. So I go back to the question and I see there's a clue, a reciprocal transformation on the y variable. So we'll go back to our data in the spreadsheet, and I'm going to put in a new column which I'll call TD for transform data, and the relationship that I'm looking for is 1 over, that is the reciprocal, of the y variables, which I've got stored in XP. We can see the numbers, but now let's have a look at what the graph looks like. There's my original non-linear. Let's change it to the transform data, TD, and we get something that looks remarkably linear, as the question suggested. So now what we do is come up with an equation for the transform data. I'll do some regression, and the calculator's given me the equation. Now all I need to do is remember that that is 1 over y. So here's how I'm going to write my equation. I'll express it as 1 divided by y, or the reciprocal of my y values, equal to, and I can pick up the equation from my variable list. It's under stat regression equation. It needs a variable, x, and then press enter. Note that my equation is in the form 1 over y equals. It's possible that answers could appear as y equals, so you may need to solve for y. But in this case, we can see our equation sitting in option E. Question 8. We're still using the same data. In fact, this question asks us to use the same equation that we've just determined. It wants the value of y when x is equal to 5. So what we'll do is we'll choose the solve command. We'll grab our previous equation, request that we're solving for y. Given that, which is the little vertical bar in the control equals template, given that x is equal to 5, we get the answer 18. So the closest answer to that is option A. Question 9. In this question we're being provided with a table full of statistical analysis for some bivariate data involving the variables x and y. We're required to work out the value of r, the correlation coefficient. To do this, we need to know some important formulas. The fact that the regression equation is given as y equals a plus bx, so we know the value of b, and on our formula sheet we have the relationship b equals r times the standard deviation of y over the standard deviation of x. So I'll use the solve command. I'll enter the values 1.52 for b, equals r times the standard deviation of y divided by the standard deviation of x, and then solve for r. I get an answer of 0.996, which is option C. Question 10. We've been provided with 9 weeks worth of sales data for ice creams. The question asks us to find the smooth number of ice creams sold for week 5, and we're required to use 4-mean smoothing with centering. So that works by taking an average of consecutive 4-week blocks. The problem as we take those averages is that they don't align perfectly to any middle value. You can see the 242.75 is between week 2 and week 3. So we solve that by taking an average across the corresponding weeks. So let's see how we do that on the calculator. Okay, so I've preloaded the data from the table. We start by inserting a formula the same as you would on any spreadsheet. I'm going to use the list operations and collect the term mean. I could have typed it. And then I use cell references, again the same as a spreadsheet, B1 semicolon to B4. That'll give us 4 points. You can see, of course, cell C2 is somewhere in between. So now what I want to do is fill that formula down. I don't need to keep typing it. I use the fill operation, arrow down, and press enter. So now I've got a 4-point mean. Now I just need to center it. That is, take the average of consecutive values in column C. So I'm going to use the list maths again, select mean, and I want the average of cells C2 and C3. Next, I'll fill that down. And now the value that I'm looking for will be in cell D5, that is 329, which aligns to option C. Question 11. We've been provided with the same set of data. This time we're asked for the smoothed mean for week 3 using a 3-mean smoothing method. This one's much easier. In fact, we can do this directly on the calculator application. We calculate the mean by typing in the numbers directly, 197, 240, and 245, and then divide by 3. Of course, I could have used the mean command again, but I've got my average, 227, which is closest to option B. Okay, question 12. The quarterly sales for a business in millions of dollars in 2017 to 18 are displayed in the table. Using these sales figures, we need to find a seasonal index for quarter 2. Now remember, to calculate the seasonal index, we take the average for each year and then the value in each quarter divided by the average. That is, it's a comparison between the existing month and the yearly average. So let's see how to do that on the calculator. Okay, to save time, I've already entered the data. I've titled the lists year 2017 and year 2018. Now I do need to calculate the average for each year, but I'm going to do this in a notes application. I could use absolute cell references in the spreadsheet, but let's have a look at the notes. Control M puts in a math box. I'll set M17 to represent the mean or average for the year 2017. I could select the term mean from the menu or the catalogue, but I've just typed it in. I'll do the same for the year 2018. So M18 will be assigned equal to the mean for the year 2018. You're going to see the advantage of doing it this way in just a moment. So, I've got my averages. Now watch what happens. If I go back to the spreadsheet and I change any of the values in my data, so I'll change cell B4 to a 1, we see that the mean has automatically updated. Let's go back and fix that back up again. So now I can reference those values, M17 and M18, in my spreadsheet because they're in the same problem. So I need to do 1.74, the first quarter value, and divide that by the yearly average, which is M17. Then I can just fill that formula down. If I was using absolute cell references, I would have needed some dollar signs and all sorts of things. So this is kind of a cool way to do it just on a calculator, and a neat use of the notes application. So I've got my seasonal indices for the year 2017. Now I've got to get them for the year 2018. Oops, looks like I've got two equal signs there. Let me just fix that. And then once again, I'll fill those figures down. So now I'm going to have the seasonal indices for the year 2018. Now I need to calculate the average seasonal index for each quarter. For us, that's just 2 years. So I'm going to do C1 plus D1 and divide it by 2. There's my average. Now I can grab that value and fill down. Now we need the seasonal index for quarter 2, so that's a value of 1.4, which I believe is option C. Okay, question 13. The value of an annuity investment where interest is paid monthly and payments are also paid monthly can be modelled by the following recurrence relation. We see the initial deposit, V0, is $56,000, and we need to find the value of this annuity after 3 months. So we can do this directly in a calculator application. We could do it in a spreadsheet, but for 3 months it's just as easy to do it directly in the calculator. So there's our recurrence relation, just a little comment, and I'm going to type in 56,000 and just press enter, nothing else. This stores it in a variable called answer. So now I can type in my recurrence relation and press Control with the negative sign, which is answer, and then plus 500. Press enter. That's the balance after 1 month, then 2 months and 3 months, and I'm just pressing enter each time. So the result, 58,232, which is option E. Okay, question 14. We've got the same annuity, and all we're looking for this time is the increase in the annuity between the 3rd and 4th month. So all we need to do is continue our previous calculations, press enter once more, then go up and collect the value for the 4th and then the 3rd month and find the difference, $750, which is option B. Okay, we're getting to the end. Question 15. A car is purchased for $35,000. Over time, its value depreciates using the reducing balance method. The reducing balance method is depreciating at 7.1% each year. I'm not even going to reach for the calculator for this one, because essentially what we're looking at the end of each depreciation period is the other 100% of the vehicle. So looking at those values, that would be 92.9% or 0.929. So the answer's A. Okay, question 16. We're using the same vehicle, same depreciation, and we're just looking for what is this car worth in 5 years' time. So we're going to use our recursive relationship that we established in the previous question. So once again, I'll enter my original value, 35,000. By doing that, it's storing it in answer. Then I can use the answer command and multiply by 0.929. That's the balance after each term. So after 1 year, 2 years, 3 years, 4 years, 5 years, we see the value is $24,218, which is answer D. Question 17, still looking at the same vehicle, and we're looking for the depreciation of the vehicle during the 5th year. So it is the value of the car at the end of the 4th and the end of the 5th. So we're just looking for the difference. To do that, we'll go back to the calculator and just subtract the two values. So the answer is $1,851, rounding it off, corresponding to E. Okay, question 18. Jane borrows $250,000 towards the purchase of a house. To pay this loan off, she makes monthly payments, an interest rate of 3.5%, compounding monthly, and she wishes to pay the loan off in 25 years. This looks like a job for the finance solver. So we start by entering the value for N, which is 25 years and 12 payments per year. The interest rate is 3.5%. Our principal value, $250,000. Final value is 0. Payments per year is 12. Compounding periods per year is 12. Arrow back to the payment amount and press enter. We see the payments of $1,251.55, so rounded $1,252, which gives us option B. Okay, question 19. 2 questions to go. Jane's still got the same amount of money, but this time we're interested in the balance of her loan in 10 years' time. So we'll go back to our finance solver, which, by the way, conveniently holds all the previous variables. So we need to look at 10 years, so that's 10 by 12 payments per year. Interest rate's the same. Our principal value is still the same. She still borrowed $250. Now we're assuming that the payments at $1,252 per year are still there. 12 payments per year and 12 compounding periods per year. But this time we're interested in the final value. So it's $175,072 rounded off. If you're wondering about the negative sign, that's because it's a debt. It refers to the different direction that the money is going. So our answer is option C. Now, question 20, final question. After 10 years, the interest rate changes to 3.4%. We need to find the new repayments. So we return to our finance solver and we use 15 years remaining on the loan at 12 payments per year. We change the interest rate to 3.4%, but we also now need to change the principal value. The principal value now becomes the balance that existed after 10 years. We skip past the payment because that's what we're going to calculate. We set the final value as 0, leave the payments per year and compounding periods per year as 12, and we see the final balance. And our final answer, option A. That's all for this webinar. Hope you enjoyed the questions, hope you went well, and we wish you good luck with your exams. And if you're looking for some more revision, please check out the other tutorial series that we have on our student website at education.ti.com/Australia. Thanks for watching.